Oh, I could watch this strip forever. But we won't because we need to talk about limiting reactants. Pulling it all together. A limiting reactant is a reactant which is completely used up in a reaction. This reactant that gets completely used up limits the amount of product formed because it runs out. Once that limiting reactant is out, there is nothing else to react with the other reactants to form our products. So we use the idea of limiting reactants quite frequently, and the grocery store banks on this. And I don't know, it really makes me upset. So let's just say, for our purposes, I am planning yet another birthday party for yet another one of my offspring. And we want to serve cheeseburgers. So I'm going to need to make everybody a cheeseburger. We're balancing an equation right now. I know that each person will need one patty, one bun, one slice of cheese in order to make one cheeseburger. It's a 1-to-1-to-1 ratio, okay? However, when I go to the store to buy these things, they're not sold in packages that are equal to each other, okay? I can buy a package of 12 patties and 8 buns and 11 slices of cheese. That is math I cannot do at the grocery store, people, okay? Just taking a look at these, it looks like the buns are in the least amount. If I were to get one package of each of these, I am limited by the number of buns I have and how many cheeseburgers I can make if everyone's going to have one patty, one bun, one piece of cheese. Okay? Even though I have 12 patties and 11 slices of cheese, I can only make 8 complete cheeseburgers because those hamburger buns are my limiting reactant. And I swear to you, the grocery store is doing this on purpose. So here's my conundrum. I got a party. 32 people are coming. So I know I'm going to need 32 cheeseburgers. Okay? So at minimum, how many of each of these packages am I going to have to buy? Well, considering this is my limiting, okay, 32 divided by 8 is 4. I need 4 packages. Okay? 32 divided by 12, I don't even know this math. 32 divided by 12, I'm going to need 2.6. Okay, I need 3 packages of hamburger patties. There's going to be hamburger patties left over. 32 divided by 11, we'll just see what the actual math is. 2.9. Let's just round up to 3. I'm going to need 3 packages of the cheese, and I'll have 1 slice left over there. So I'm going to have 2 reactants or 2 parts of my recipe that are in excess, and we have 1 that is our limiting reactant. So we deal with this idea of limiting reactants all the time. And what we've essentially done is we've figured out what our limiting reactant is based on how many cheeseburgers we're trying to make. Applying this to chemistry, we can look at this beautiful visual model when we react hydrogen with oxygen. So we have 2, 4, 6, 8 hydrogens and 3 oxygens. We can see that oxygen is our limiting reactant, okay, because we run out of it. And we see that hydrogen is in excess because there's extra left over after this. But unfortunately, we can't look at the atoms and we can't just see what's left over afterwards. We have to approach this mathematically. You know me, I'm a huge fan of showing you the steps. So these are the steps to find the limiting reactant. You're going to start where we always start, always with a balanced equation. Then, this is important, you're going to choose one product to compare both of your reactants to. One product. If you compare both products, that becomes very challenging. You're comparing apples and oranges. So pick one product, and you're going to compare both your reactants to that product. You're going to solve for moles of the product for each reactant. This will make more sense when we do this. So you're going to have 2 calculations. So you'll take your grams of one reactant, convert it to moles, and figure out how much the one product you can make. And then you'll do the same thing for the second. You'll take the second reactant's grams, convert to moles, figure out how much product you can make. One of those products is going to be made in a lesser amount. That tells you what your limiting reactant is. Let's practice. Okie dokie. Okay, we have our list of how-tos right up here. I love referencing those. I highly recommend referencing until you don't have to, until you know the steps by heart. And that's a way to memorize something in practice and in application. It'll be much more meaningful in your life, maybe. I don't know. Okay, so we're given a reaction. I love, love, love when they give me a balanced equation. We're going to determine the limiting reactant if you start with 79.1 grams of zinc and you react that with 161 or 63.1 grams of HF. Okay. So we have the balanced equation. Check. We're going to choose one product to compare. Ooh, I'm going to be lazy on this one. Check this out. Not much writing to do with that one. So we're going to compare this. We're going to solve for moles of each product or of each reactant. Solve for moles of product for each reactant. Okay, so what we're going to do is we're going to go from grams of zinc to moles of zinc, and then we will convert to moles of our product. Okay, so this is going to require a mole ratio because the substance changes. You see the substance changes from zinc to H2. And we're also going to do the same thing for grams of HF. We're going to convert that to moles of HF. And then eventually we'll use a mole equation, mole ratio to convert substances. So there's our mole ratio, okay, because we're changing from one substance to the next. All right, we have our unit maps. We are ready to plug in some actual numbers. So on my first T-chart, I'm starting with 79.1 grams of zinc. I need to convert that to moles of zinc, so I'm going to need to look at the periodic table to see what the mass of one zinc is, and that is 65.39 grams of zinc. And I'm putting that on the bottom so grams will cancel. And now I have moles of zinc. So now I'm ready for the mole ratio. I want to cancel moles of zinc, so I need to put the moles of zinc on the bottom, and I want to find moles of the product that I've chosen to compare, which is H2. Looking at my balanced equation, I don't have any coefficients, so this is a 1-to-1 ratio. I now have moles of H2, so I'm finding the theoretical yield. If I start with 79.1 grams of zinc, this is theoretical yield. Multiplying across the top, dividing by the bottom, you wind up with 1.21 moles of H2. There's no need to convert to grams unless they ask you to convert to grams. Okay, let's do our next equation because we need to see, starting with 163.1 grams of HF, how many moles we're going to produce of H2. So we're doing the exact same thing, but with the other reactant. One of these is going to produce less. That's my limiting reactant. So to go from grams to moles, I'm going to use the molar mass. So adding up 1 hydrogen plus 1 fluorine, the mass is 20.01 grams. I'm putting this on the bottom because I want to cancel grams and I want to be left with moles. When I have moles, I am ready for the mole ratio. So this time moles of HF are going to go on the bottom. Looking at my balanced equation, it's 2 moles of HF per 1 mole of H2 that's produced. Okay, well, this is great. I'm at moles of H2. This is something I can compare between them. I'm going to multiply across the top, multiply across the bottom, and then divide the top by the bottom, and I get 4.08 moles of H2. So let's take a look at this real quick. We have zinc producing 1.21 moles, and we have HF producing 4.08. So zinc is actually producing less, which means that zinc is going to be my limiting reactant.